want to welcome you to my to a topic called principal component analysis. Okay, like I said, this is like a formal introduction to principal component analysis. Of course, I'm actually going to walk you through theoretical development of principal component analysis. I'm also going to walk you through how you can actually implement that using a software. Okay, so let me tell you that with the principal component analysis, uh, if you look at our data set, okay, data set in a multivariate setting, okay, actually we got p number of variables that are actually observed on n experimental units. Okay, of course, by now you know statistical architecture. Okay, the statistical data structure. You know the data structure of multivariate analysis. You know of the multivariate. Okay, we know the data structure. We know the way multivariate data structure look like. Okay, let me tell you this. The goal, the essence of principal component analysis, I'm actually going to tell you today. I want to confirm to you that the principal component analysis is a dimensionality technique, reduction, okay? Dimensionality, okay? A dimensionality reduction technique, okay? Now, we call it a dimensionality reduction technique because it's actually going to ensure that the dimensionality in the data set is actually reduced. And let me tell you something. When I say dimensionality in the data set, of course, I'm actually going to have n by p, okay? Because I collected variables, over so many experimental units. Of course, you know that that dimension is going to be so huge, okay? So when the dimension is huge, you're actually going to have like so many set of independent variables, okay? And what we actually need to do, we need to have a way to reduce the dimension because, uh, in statistical analysis, when when we have a reduced dimensionality, it's actually going to be so easy to undertake, okay? And that is the reason why we actually need a technique that will enable the dimensionality in the data set to be reduced. But let me tell you this: there's going to be a price that needs to be paid when you are trying to reduce the dimensionality in the data set. The only sacrifice here is that we're actually going to sacrifice little accuracy because we know that when the dimension is being reduced, there's going to be loss of information. But you know what? The principal component technique will ensure that the largest amount of information is actually going to be retained. Okay? The principal component analysis does it in a way that we are able to retain even after transforming the large sets of variables into smaller ones. It does that in a way to retain the largest percentage of information in the data set. But the fact remains, the little amount of information will actually be lost in the process. Okay, so and that was why I said the principal component analysis is a dimensionality reduced technique. And that was what I was trying to say right here, that fewer linear combination K that are explain large portion of the total variation than the number of variable P. Okay, so because it's actually going to do that in a way that these are drastically reduced. okay? And then if they are reduced, of course, the information, the largest percentage of information will still be retained, okay? And you know what? Uh, if so, if that is actually going to be the case, then the question now is, what are the steps that we actually need to follow, okay, in constructing principal component analysis? I'm going to share something with you right now. I'm actually going to share something with you right now. I'm going to have a new share with you. I'm going to share my whiteboard because I actually want to, uh, you know, uh, explain some things to you. Now, do you remember yesterday? Can you guys see my whiteboard now? Can you guys confirm if you are seeing my whiteboard now?
Yes.
Okay, thank you so much. Now, let me tell you, yesterday, I I told you that in a multiple linear regression, when predictor variables are correlated, the use of principal components can also be adopted, okay? So principal component does not only perform that job, it also perform a job of of reducing the dimensionality in the data set, okay? So which is to confirm to you that the principal component actually perform more than that role, more than what we did yesterday. And that is the reason why, what we want to focus on today is how we can actually use principal component analysis to reduce the dimension of the multivariate data set. Okay, so the question now is, if I have a multivariate data set that I'm also going to show you today, in our, what are the steps that we actually need to take? Okay, number one, the very first step that we need to take is we need to data standardization. Okay, I'm going to call it standardization of the p variables. Okay, standardization of the p variables. When I say p variables, of course, I'm actually talking about, the independent variables. Okay, we actually need to standardize them. Now, why do we need to standardize them? I'm going to tell you now. We actually need to standardize them because the variables that we collect may actually be in different units. Okay, they're actually going to be in different units. And you know what? Some of the variables may actually have a range that is different from others. Okay, and those who have a wider range will dominate the others. I'm going to say that again. The reason why we need to standardize the independent variables when we are working on the principal component analysis is to, is to make sure that, that any of the variable does not really dominate the other variable, because since variables that we collect, they are in different units, they actually need to be scaled. Okay, they need to be standardized. Okay, and the moment they are standardized, of course, those who have the wider range, okay, we not after standardization, they will not be able to dominate. Okay, and that is the reason why we actually need to start by standardizing the variables. Now, the next thing we actually going to do after standardizing the variable in step 2 is, setting up, is setting up of, of variance covariance matrix. Okay, setting up of variance covariance matrix. Okay, the setting up of variance covariance matrix, or you can simply call that covariance matrix. Okay, you can simply call that covariance matrix. Okay, so some of you may want to ask, I think I've told you the reason why we have to go through the standardization. Okay, now the question is, why do we need to set up a covariance matrix? We actually need to set up a covariance matrix because the covariance matrix will enable us to measure the expansion, okay, the deviation of the mean of the input variables, okay, around the the data point in the variable. Of course, you know that, okay. We know, I could remember when I was walking you through the statistical theory where we actually go from uh, deviation matrix to a sum of square product, and then from a sum of square product we find ourselves in a variance covariance matrix. I think you remember that we did that before, and the essence of the covariance matrix is just for us to be able to measure the expansion, okay, the deviation, okay, of the the mean of the input variable from the respective observation. Okay, and that was the reason why we actually need to set up a variance covariance matrix. Let me also tell you, alternatively, you know, alternatively, alternatively we use correlation matrix. Okay, alternatively we use correlation matrix. You remember yesterday when we were trying to solve the problem of multicollinearity in a multiple linear regression. We actually found correlation matrix, and then the inverse of the correlation matrix, the diagonal element in the inverse of the correlation matrix actually give us what we call the eigenvalues. Okay, so so alternatively we can use correlation matrix, but in most of the time I think we actually normally want to use the variance covariance matrix. Now you know the reason why we are actually going to consider the variance covariance matrix. Okay, now it's actually going to be the variance covariance matrix of the standardized p variables. Okay, it has to be the the variance covariance matrix of the variable that have already been standardized. Okay, I think you really understand how that now. Okay, the next step right here is actually going to be, after having the covariance matrix in place, the next thing is the computation. We're actually going to have the computation of the eigenvalues and the eigenvector. Okay, the eigenvalues and the eigenvectors. Okay, that's exactly what we're going to have. Okay, and you can see, so because you know why we need to do that? Because the eigenvalues that we're actually going to compute will serve as the variances of the transform variables. I'm going to say that again. The eigenvalues will actually serve as the variances, okay, the variances of the transformed variables. Okay, why the eigenvectors that we're actually going to have, the principal components that we're actually going to derive, will basically based on the, the agent vector values. Okay, so I'm going to say after number 3, then we can now obtain, okay, the principal components. Okay, so what I'm going to do today, I'm actually going to show you. uh, I already, in I've attached to this material, I've attached, some arrow codes, but I'm actually going to show you an example of that. So what you just need to do, when we are done with the lecture, you can actually run that on your own, and you're actually going to see. Okay, so these are 4 ways, 4 steps that you actually need to follow. Okay, when you want to, construct, when you want to construct or get a principal component analysis, on the set of variables. Okay, with the attempt to reduce the dimensionality, okay, in the data set. Okay, can you guys see the steps right now? Can you guys see the steps?
Yes.
Okay, thanks for sharing. Thank you for that. I really appreciate that. Okay, now so that is going to be the end of my share for this one. I'm actually going to go into a different one now. Okay, so I'm going to go into a different share right now. Now you can now see, so I've been able to explain this. Okay, so that is the job of the principal component analysis. Okay, so this is a population principal component. Okay, this is the way we got P number of variables. Okay, and I told you we're going to set up a variance covariance matrix. Okay, I just told you right now that you're actually going to set up a variance covariance matrix, and of course from the variance covariance matrix you're actually going to find the agent values. Okay, and you know what, the agent values are the variances, okay, of the new transformed, of the new variables. Okay, the variables have now been transformed. Okay, the agent values, we're actually going to be the variances of that. Okay, and you know what, this is like arranging the agent values from the largest to the smallest. Okay, the agent value from the largest to the smallest, because the lambda 1 right here is actually going to be the variance of the largest principal component. Okay, because the largest principal component, we have the largest amount of variation. Okay, so I'm actually going to walk you through that, in R. Okay, you're going to see that. I'm going to show you. I'm not going to implement that with you in R. You're going to run that for yourself. But you know what, I'm actually going to have, I'm going to show you some stuff. Okay, now do you know that the new variable that we derive is actually going to be y1 up to yp. Okay, and you know what, the new set of variables that we have, okay, will be a linear, each of the new set of the variable will be a linear combination of the whole variables. I'm going to say that again. The new set of variables, okay, the initially we got a x1, x2 up to xp. Okay, that are the set of variables. Okay, maybe they are highly correlated. Okay, or we actually want to reduce the dimensionality. Okay, like I told you, principal component does to function. Okay, it reduces dimensionality in a data set. That's number one. Number two, it can help to convert, variables that are correlated to uncorrelated ones. Okay, so what I'm trying to tell you right now, if I got p number of variables, then the new variable that I'm actually going to have, I'm also going to have p numbers of them. And you know what, each of this variable each of this variable is a linear combination of the whole variable. That's exactly what I'm trying to talk about right here. And in matrix form, this is exactly what we have. Okay, and you know what, the variance of each of the variable, okay, the variance of the transformed variable, the variance of the transformed variable is what I'm actually showing you right here, okay? And you know what? This is the covariance of that, okay? And you know what? The first principal component is a linear combination, just like what I'm trying to tell you right here, okay? Now, before, you know, for all what I'm trying to talk about here, you know, to have a meaning, okay, I'm still going to take you to the application, okay? These are just theoretical development, okay? Now, take a look at what I have right here, okay? You know, I told you the other time that if I have, you know, p number of variables, I'm actually going to construct variance covariance matrix, and I'm actually going to get, you know, my eigenvalues and the eigenvectors. And with that, I'm actually going to set up my principal component, okay? And from there, after getting that, then the next thing that I'm actually going to do, I may want to measure the proportion of the total population variance due to k principal component, okay? Now, what I'm trying to talk about is that if I have p numbers of variables and I'm going to have p numbers of principal components, okay? Now, if I want to measure the proportion of the total population variance due to a particular principal component, then what I'm actually going to do, for instance, if you take a look at the lambda high, lambda 1 here, the lambda 1 here is the variance of that particular principal component, okay? If I want to measure the contribution of that particular principal component, I'm actually going to say lambda 1 divided by the total number of variances, okay? You remember the other time that when you have a variance, you know, when you obtain your, you know, lambda 1 up to lambda p, the addition of the eigenvalues is a total variation, okay? The addition of the eigenvalues, if I have add lambda 1 up to lambda 2 to lambda p, then just like what I'm doing right here, the denominator right here is a total variation, okay? If I want to measure the proportion of the total population variance due to a particular principal component, I'm actually going to do the ratio right here, okay? I'm going to walk you through that in the practical demonstration, okay? Now, but quickly, for you to be able to understand what I'm trying to do, I'm actually going to walk you through a practical demonstration. Give me 1 second, and you're actually going to understand what I'm talking about, okay? Give me 1 second. I'm going to do that right away. It's loading right now, and then it's also part of the material, okay, that I've already uploaded, okay? So it's part of this material right now, but I just want to show you the practical demonstration. But I, four of us, need you guys to confirm. Are you guys seeing this material right now? Principal component analysis. Can somebody confirm that before I go ahead?
Yeah.
Yeah, thank you very much for confirming that. Okay, now what I've been explaining to you so far, I want us to have a practical demonstration of that using the R software. Okay, like I said, I'm not going to make use of the R studio or interface today, but I've already prepared a code for you that you can actually run. Okay, and I want us to use a data set. Now, when you take a look at this data set, I got 20 engineer apprentices, okay, and 20 pilots. We're given 6 tests. Okay, the data set that we want to use, 20 engineer apprentices and 20 pilots were given 6 tests. Okay, the data were obtained from the companion FTP side of the book Method of Multivariate Analysis by Avin and Rencha. Okay, the tests measure the following attributes. Okay, the 6 tests that I talk about: intelligence, okay, form relations, uh, you know, dynamometer dotting, sensory motor coordination, and preservation. Okay. Now, if you take a look at this, we're going to have a lot of data set. Okay. Now, let me show you the data set right here. You're going to see the data set right now. Uh, if you copy this into R, okay, if you copy what I have here into R, okay, you are not going to have this. Okay. So what I need you to do, if you want to run this in R, you need to first, write the data set out. Okay. You need to write the data set out. Okay. Now take a look at what I have right here. We actually want to consider apprentice 1, 2, 3, 4, 5, and 6. Okay, this is the group. This is for intelligence. This is formulation. This is a denominator dotting, and so on like that. Can you see that now? So 1, 2, 3, 4, 5, 6. Okay, and you know what? This is for the 6 apprentices. Okay, so like I said, if you want to have the access to the old data set, you can actually go to the site. Okay, you can actually go to companion FTP site. Okay, to be able to have access to the old data set. Okay, but the one that I'm just showcasing right now is just having 6 number of 6 experimental units, and then we got 6 1, 2, 3, 4, 5, 6. Now, there's a question I want to ask you, and then the question is this: if the number of experimental units, okay, is the same thing as the number of predictors, I'm going to say that again. If the number of experimental units is the same thing as the number of predictors, there's going to be a problem. Can somebody tell me the problem? If the number, like you're doing in a multiple linear regression, okay, and then if the number of experimental unit, that is the number of observation, okay, if it is the same as the number of predictors, okay, can somebody tell me what may happen? Okay, can somebody tell me? If the number of experimental units and there's something I want to I'm going to go back. Give me 1 second. I'm going to show you something again, so that I want you to see something right here before, so that you'll be able to know the kind of response you're likely to give me. Okay, give me 1 second. There's something I'm going to show you right now. Oh, okay. I think I show you that in let me see. I want to check whether it is in this material or the material that I attached yesterday. So there's something I quickly want to show you so that it's actually going to make sense to you. Okay, so it is not in this material, but the one, let me check the one I showed you yesterday when we were dealing with a multiple linear regression, when we're dealing with the principal components in multiple linear regression. So let me just check if it is, just want to be sure if it is there. Okay, never mind. I think I'm going to tell you. So never mind. I think I'm going to tell you. Now, this is what I want to tell you. Okay, what I actually want to tell you is just that if the number of predictors and the number of experimental units are the same, it's going to create an estimation problem. If you take a look at what I have, can you guys see what I'm projecting right now. Can you see apprentice? Can you see that? Group intelligence, can you see that?
Yeah.
Okay, so the number of experimental units here is 6, and the number of predictor is 6. Okay, now if you look at what I put here, I said the variable appear to be measured in different units. You know, I told you the other time, if you look at intelligence, the unit for intelligence is different from the unit of formulation, it's different from the unit of thermometer, is different from dotting and so on like that. Okay, and I told you when I with my introduction that because of the reason why we need to standardize, okay, the reason why we need to standardize is to be able to ensure that the predictors that are in different units, okay, will not dominate, okay. They, you know, because when they are in different units, they are likely to have a different range. Okay, look, take a look at this. The range of intelligence is actually from 77 to 140. Okay, but look at the range for formulation. The range of formulation is from 22 to 49. Okay, so we don't want a situation whereby the intelligence we actually dominate this, and that is the reason why we actually need to standardize. Okay, and when we standardize, okay, when we standardize, then we can obtain the variance covariance matrix or the correlation matrix, and that's exactly what I'm trying to talk about right here. Now you can see my data set right now. This is my data set. Okay, with this data set right now, of course I can do multivariate analysis. Okay, so like I said, uh, the very first thing, so after standardizing, look at what I'm going to do. When I write this code, can you guys see this code right now?
Yeah.
Okay, so take a look at this code right now. COV, that's a code for covariance. Okay, this is just what I use to, you know, save my data. Okay, so when I do the when I find that, I'm actually going to have this. So what I have right here now is a variance covariance. Okay, this is going to be variance covariance. Okay, and let me tell you, if you count at 1 2 3 4 5 6, it's going to be 6 by 6. Okay, it's going to be 6 by 6. What I'm showing you right now is actually going to be 6 by 6 matrix. Okay, now after having the variance covariance, okay, uh I want you to see something right now. Like I said, you get your variance covariance, and after having the variance covariance, of course, uh you remember the other time that you're actually going to obtain the agent values and the agent vectors. Okay, now take a look at this. If I want to write, if I want to compute the agent values and the corresponding agent vectors of X, I'm actually going to write whatever I'm going to write agent X. What is my X? My X right here is a variance covariance. Okay, my X right here is a variance covariance matrix that I've already derived. Okay, is a variance covariance, and you know we always want to find the agent values of the variance covariance. Okay, we can the agent values of the variance covariance. Okay, I think you get it now. Okay, so if you take a look at what I have, give me 1 second. Oh, okay, I think it's loading. Okay, so as you can see right here, because I got 6 variables, I'm actually going to have 6 agent values. I think you know that 1, 2, 3, 4, 5, 6. Okay, and you know what? For each agent value, I'm actually going to have agent vectors. Okay, I think you can see that now. These are my agent vectors. Okay, corresponding to each of these agent values. Okay, and you know how I compute them. Okay, if I want to have the agent vectors and agent values, I'm actually going to write agent. Look at that agent of the covariance matrix. Okay, the agent of the in R agent of covariance matrix will actually give me you know, and by the time you write this guy, you're going to, you know, dollar values is going to give you the agent values, and dollar vector, you're actually going to have your agent vectors. Okay, now after having the agent vectors and the agent values, what is the next thing that we actually we want to do. Okay, the next thing that we want to do, the eigenvectors represent. What is the meaning of eigenvectors? The eigenvectors represent the principal component of X. I'm going to say that again. Eigenvectors. You know, we actually want to construct the principal component, okay? We actually want to construct the principal component, okay? The eigenvectors represent the principal component of X, okay? The eigenvalues of X are used to find the proportion of the total variance explained by the component. You remember the other time when I show you a formula, when I said if I want to measure the contribution of a particular principal component, okay, it's going to be the eigenvalue divided by the total, sum of the eigenvalues. Okay, I think you get that now. So the eigenvectors and the eigenvalues, they get a different function they perform in principal component analysis. Okay, the eigenvalues, of variance covariance matrix can actually be used to find the proportion of the total variance, okay, explained by the component. I think you get it now. Okay, so but why the eigenvectors actually represent the principal component of X. Okay, the principal component of X. What is my X? My X is a covariance matrix. Okay, if I want to get that now, this is exactly what I'm talking about. Okay, this is what I'm talking about. How do I arrive at this? This is the code that I'm actually going to write to be able to arrive at this. If I actually want to know the contribution of each, the contribution of each, the eigenvalue, of course, I'm actually, of each principal component, I'm actually going to, this is what I'm going to get. Now, if I take you back to the values of the, look at it, these are the eigenvalues, okay? These are the eigenvectors. I'm going to say that again. Now, how do I obtain this? Mathematically, how do I get the 0.5, 002739? How do I get this, okay? This is the code that I wrote, but if you want to compute that manually, you're actually going to come here. It's actually going to be this guy here, okay? It's actually going to be this guy here divided by the total number of all of them, okay? Divided by all of that, okay? This guy here, if I want to know the contribution of the first principal component, it's going to be the ratio of this guy divided by everything, divided by the total number of everything. If I want to know the contribution of the second principal component, it's actually going to be this guy divided by the total number of everything. And that's what I'm going to do for every one of them. And that was how I got this. Take a look at that. Look at that. And look at the formula right here. Can you see now? X divided by sum of that. Can you see that? So a particular principal component, a particular eigenvalue divided by the sum of the eigenvalue. And when you take a look at what I have here, the first principal component explain about 50%. Okay, the first two principal components explain about 75%, because when you add this to this, okay, you're going to have 75%. Okay, so the first two explain 75 point. Look at that. That was why I said the first two principal components account for 75.5% of the total variance. Let me tell you something. We don't necessarily need to use all the principal component, but we're actually going to use the combination of the principal component that give us the largest information, okay, out of 100%. Okay, and then that was why I was trying to tell you the other time that when you are talking about dimensionality, reducing dimensionality of a multivariate data set, it's actually going to come with a price, and the price is there's going to be a loss of little information. Okay, just very little information is actually going to be lost at the end of the day. Okay, but you know what? The principal component analysis can actually guarantee, or it can actually preserve the largest percentage of of the information in the original data set. Okay, so I think you can see that now. So that is 70. So the first two principal components are actually going to explain our 75.5% of the total variation, of the total variance. Can you see that now? Okay, so if you want to have the plot of that, this is basically the plot. Okay, now what I'm trying to tell you right now, these are the agent vectors that I talk about. Okay, these are the agent vectors of my variance covariance matrix. Okay, and you know what? Do you know that based on the agent vectors, we can actually, I told you the other time that principal component that we derive is actually going to be a linear combination of the, old variables. Okay, if I want to write, what if I ask you in exam that can you write the first two principal components out? The first two principal component I'm actually now can you guys see this right now? Give me 1 second. Can you guys see the two equations here? Can you confirm that?
Yes.
Okay. The first two principal components are this. How do I got it? I told you the other time that since I have y1 up to y6, I got 6 number of variables. I'm actually going to have 6 numbers of principal components. Okay, but you know what? We don't need to make use of all the 6. Okay, why are we using 2 right here? Because the first two principal components actually explain about 75%. Look at that. If you add, this is the percentage variation. So if you add this to this, the first two principal components already explain about 75%. And that is the reason why if I want to write a model, I'm going to use it, if I want to write the first one, the first one that explained, this is what I'm going to use. Take a look at this. I'm going to use the agent vector values. Look at that. Minus 0.211, whatever. Look at that. It's right here. 0.039, whatever. Look at that. It's right here. I'm going to use the combination of this, okay, up to minus 0.5. Can you see that now? So which means the first principal component, which is the first transformed variable that have the largest variation, okay, that are the largest variance, is actually this, okay? And the second one is this. Okay, how do I get the second one? I'm going to make use of this second agent vector, okay? This is the first agent vector. This is second one, third one, fourth one, and so on like that. Now, is there anyone who want to ask question? Is there anyone?
I have a question.
Now, go ahead.
So these y1 up to y6, are those the standardized variables or those are the original variables?
The y1 up to y6 are not standardized variable. They are the original variables.
Okay.
So, did you get it now?
Yep.
Okay, so the z1 and the z2 are the new set of variables that we're going to call principal component, that we called principal components. And of course, in exam, do you know that I can actually give you, I can start all the way from a design matrix X and ask you to actually, construct, 2 or 3 principal components. So this is going to be your final destination, okay? It's going to be your final destination, okay? And I can actually ask you a series of questions about the contribution of the first principal component. Like I said, the contribution of the first principal component, look at that, it's right here. This is the contribution of this second. So this is the contribution of the Z1, Z2, Z3, Z4, Z5, Z6, the new set of variables that we just have. Okay, so and you know what? If I have this one now, if I want to know the percentage contribution of the first principal component, this is the value. Okay, for the second, this is the for the first two. I'm going to add. Okay, for the first two, I'm going to add this to this. Okay, for this first three, I'm going to add this to that, okay? So I think you see that now. And if you actually want to obtain this, this is going to be the formula, okay? Can you see that now? So I believe today you have been, I've walked you through the process of getting a principal component analysis, okay? Like I said, before I go today, I'm actually going to tell you that principal component analysis does two function. Number one, principal component analysis can actually be used to convert variables, the predictor variables that are correlated in a multiple linear regression, okay? And not only that, it also does the job of, reducing the dimension of the data set, okay? And you know what? uh, because we actually want to attain simplicity, because if you want to analyze data set, okay, they don't need to be in a complicated nature, because multivariate data analysis are more or less in a complicated, and I mean they are so complex, okay. And a situation where you got so many experimental units and so many number of predictors, of course, the dimension is going to be so huge. Okay, and analyzing that kind of data set is likely going to be chaotic. Okay, it's likely going to be problematic. Okay, and that is the reason why the principal component analysis can actually be used to reduce the dimensionality in our data set. Okay, and what I've done today is to be able to walk you through the process of achieving that. Okay, is there anyone who want to ask questions today before I go? Is there anyone?
Can we have this file shared on Canvas?
Oh yeah, it's already. Let me show you right now. It's part of the material that I is uploaded. Give me 1 second. I'm actually going to show you right now. I put a code there, but if you also need that one, I can still share with you. But let me show you where you can. Can you guys see my new share right now? Okay, it's still loading. Okay, so it's still loading. Yeah, it's still loading. So I'm gonna show you something right now. Yeah, I'm sorry that it's taking forever loading. I don't know why it's doing that. Can you see the material right now? Principal component analysis.
Yes.
Okay, so let me just show you where I put that. Okay, I'm gonna show you right now. Okay, this is what I was talking about the other time. K less than P, keeping K less than P. Okay, component. Okay, so I think that was what I was looking for the other time. Okay, so the arrow component is this. I've already attached that. I've updated. You can check. I just updated this morning on this material. You can check it's on the module. Can you guys see this right now?
Yeah.
Intelligence. Okay, thank you. Look at that. This is what I did with you today. I put a code. These are just the code. Okay, these are just the code, and these are the two principal component that we just talked about. Can you see that now? So is there anyone who want to ask question today before I go? Is there anyone? Is there anyone who want to ask question? Uh, I want to thank everyone for attending my lecture today. I hope you enjoying it. You actually need to practice what I attached just now. For those of you who may have a trouble time on that, you can actually send a message to me. Let me also tell you that homework 4 will be graded today. I decided not to upload homework this week, and I have my reason. I'm going to tell you my reason, because you have an exam, okay? And that was the reason why I decided not to upload a new homework for this week, because you have an exam, okay? So you have a midterm 2 exam this week, and that is the reason why there are not going to be a new assignments, okay, for this week. okay, because you have an exam. So that you can have more room to prepare for your exam, okay? So that is the reason why I've decided not to upload new assignment this week. And then your homework 4 will be upgraded today. Check the module, you're going to see your result for the homework 4, okay? And some people seek extension for homework 5, which I think I've granted, okay? And if there's anyone who want to maybe ask 1 or 2 questions, you can actually can send a message to me. I want to apologize. I later saw some people's some student messages in a spam box. I think I need to be checking my spam box now, because some messages do go into the spam box. So I'm going to be checking that now. In case you have been sending messages to me before and you've not been seeing my reply, I apologize for that. Now I'm going to be checking my dashboard. Okay, so my spam box. Okay, so thank you for attending my lecture today. Make sure you stay safe and do have a good day.
Oh, sorry, Professor, just a quick question.
Okay, go ahead.
Maybe I missed that. So when will we have midterm 2?
Yeah, I need you to check the syllabus. I think I put the date. I think maybe around July 17, or you can check check the syllabus. Do you have access to syllabus?
Oh, yeah, sorry, I haven't checked it. Okay, thank you.
Okay, please just check on the syllabus, because I don't want to give you a wrong date. So because we are strictly following the syllabus.
Oh, okay, thank you.
So if you cannot find it on the syllabus, I think it should be there. So if you cannot find it, then you can send a message to me.
Okay, thank you.
Okay.
Professor?
Yep.
Will there be a practice exam posted?
Yeah. Oh, you talk about practice exam, right?
Yes.
Okay. So this time around, what I'm planning to do, 2 days to your midterm, like tomorrow, I'm actually going to have a practice question. I'm going to go, walk you through a practice question, okay, for the midterm. Does that make sense?
Yes. Thank you.
Okay. And that is what I will always do before my exam, even before final, before any of my exam. There's always going to be review, okay, practice question review, okay. So in the absence of other questions today, I want to thank everyone for attending my lecture. Make sure you stay safe and do have a good day.
Thank you.
You're welcome.
Thank you.
You're welcome.